Hi students, now in this video lecture we will go through topic abnormal molecular masses or abnormal colligative properties. And we know that colligative properties are those properties that depend on the number of solute particles, right, and not on the nature of the solute. Now before this video lecture we have gone through the colligative properties one by one, right? It's elevation in boiling point, depression in freezing point, then we have relative lowering of vapor pressure, osmotic pressure, right? And we mentioned that when we deduce the relationship between molecular mass of solute and the depression in freezing point or elevation in boiling point, right, we said that this relation, right, was applicable. The relationship was, if you remember, this is molecular mass of solute, right? If let's take example of elevation in boiling point, I'm sorry, it's weight of solvent, weight of solute, right? Then we have Kb, ebullioscopic constant, and 1000, right? This was the relationship between molecular mass of solute and colligative property elevation in boiling point. And we said that in this case is only applicable when the solute is non-ionic, right? That is, the solute will not undergo dissociation in solution, right? And the non-volatile, non-ionic solute was like sugar molecule. When 1 mole of sugar molecule was dissolved in water, it remains as 1 mole of sugar molecule, right? And the theoretical value of colligative property was due to 1 mole of sugar molecule, right? And experimental value of colligative property in solution is also due to 1 mole of sugar molecule, right? Because 1 mole remains as 1 mole, it will not undergo any change, right? Because it's a non-ionic. Suppose now we take an ionic salt. Let's take sodium chloride. If we take 1 mole of sodium chloride and dissolve it in solvent, this 1 mole of sodium chloride will dissociate into sodium ions and chloride ions. Or in other words, we may also say it as 1 molecule of sodium chloride, which is 1 particle, will form 2 moles, right, which is of 1 mole of sodium ion and 1 mole of chloride ion. So 1 particle of sodium chloride will dissociate into 2 particles, which is sodium ion and chloride ion. And we said that the colligative property depends on the number of particles. So in this case, the colligative property in solution where the number of particles has increased would be different, right, compared to the theoretical value, which was due to 1 particle of sodium chloride. But in solution it undergone dissociation to produce 2 particles of sodium ion and chloride ion, right? So the observed value of colligative property is due to 2 particles, right, which is increased. In case of dissociation, the colligative property will increase, we say, right, because the number of particles in case of dissociation is increased, so the colligative property has increased, right? So if the colligative property, if you check this relation, the molecular mass is inversely proportional to delta TB, which is the colligative property. So if in case of dissociation, if the colligative property will increase, the molecular mass will decrease, right? So let's take an example of this. Let's take an example of sodium chloride. If we add sodium chloride is an ionic solute. When this is added to water, it will form sodium ion and chloride ion. So 1 particle will form 2 particles, right? So here the theoretical value was due to 1 particle, right, and the observed experimental value was due to 2 particles. So the colligative property is increased. So when colligative property will increase, the molecular mass will decrease. So now let's see how the molecular mass will decrease. We know that the molecular mass of sodium chloride is it's 58.5, right? And the molecular mass of sodium and chloride ion was found to be 29.25 and 29.25. This is the observed value, right? So here the molecular mass is reduced, right? Molecular mass is reduced for sodium and chloride ions. For the particles that resulted on dissolving sodium chloride in water, for those particles the molecular weight is less, right? But due to increase in the number of particles, the colligative property has increased, right? So we say in case of dissociation, if you take other examples also, like let's take example of calcium chloride. Calcium chloride will dissociate to form 3 particles, calcium ion plus 2 chloride ions. So in this case also you will see observe the increase in colligative properties and decrease in molecular mass, or right? So in case of we deduce from this explanation that in case of solutes that undergo dissociation in solution, the colligative property will increase due to increase in the number of particles, but the molecular weight will decrease, right? Because colligative property and molecular weight we know are inversely related, right? And you can see from this observation also that the molecular weight will decrease. Now let's take another example. Here the solute undergone dissociation. Now let's take another example of acetic acid in benzene. When we add acetic acid in benzene, acetic acid will undergo association, right? The different molecules of acetic acid will unite or associate to form a bigger particle, a bigger molecule, right? So if we add 2 molecules of, if we dissolve 2 molecules of sodium chloride, if we dissolve 2 molecules of acetic acid in benzene, right, the molecules, we know that there is hydrogen bonding, right, between acetic acid molecules. This is hydrogen bonding, right, between the molecules of acetic acid. So it forms a dimer, right? So here 2 particles, right, undergone association to form one bigger particle. Yes, one bigger particle. So here the number of particles have decreased, right? Since the number of particles decreases, and we know that colligative property is directly related to the number of particles. If particles will decrease, colligative property will also decrease, right? So here if you take example of this again, we know that molecular mass is inversely related to colligative property. So if colligative property will decrease, the molecular mass will increase, right? So we can check this relation between colligative property and molecular mass from here. We know that the molecular mass of acetic acid is 60, it's around 60, and the observed molecular mass of this dimer was found to be 120, right? So here we observed in case of association, when 2 molecules of acetic acid associated in benzene, we observed that the colligative property decreases due to decrease in the number of particles as association has taken place, and the molecular mass will increase because the colligative property has decreased, right? And both these are inversely related, we know that. Now let's just read. We have just taken down all this that I have explained here. You can just take down notes from here. In case where the association of solute takes place in solution, example acetic acid in benzene, acetic acid undergoes association, right, like this, to form dimer, trimer, tetramer, resulting into lesser number of particles, right, which results in decrease in colligative properties, right? So now there's another thing that we will go through is Van 't Hoff factor, right? Van 't Hoff introduced a factor, right, called as Van 't Hoff factor to account for the colligative properties, to account for these kind of abnormal colligative properties, wherein due to association or dissociation, the colligative property is changing due to change in the number of particles, right? So this Van't Hoff factor can also be used to calculate the extent of dissociation and association. Like the association and dissociation that we have discussed here, using Van't Hoff factor we can also calculate the extent of association and dissociation, right? And this accounts, I repeat, this Van't Hoff factor accounts for the extent of, the Van't Hoff factor accounts for the abnormal colligative properties that we have just discussed due to association and dissociation, right? And one more important thing is the equation for colligative properties are changed in case of these kind of scenarios. In case of these abnormal colligative properties, the equation for the colligative properties which we have gone through before is changed, right? Is just modified. The equations would be modified by, and we'll introduce Van't Hoff factor in that, which accounts for the colligative properties, right? Delta, we know that elevation in boiling point was delta TB is equals to kBm, and we said that the delta elevation in boiling point is directly proportional to this concentration of solute, right, which is the molality. It's directly related to the molality of solution. Similarly, depression in freezing point is also directly related to molality or concentration of solute, right? So here, and same as with osmotic pressure, we will introduce the I factor. I is Van't Hoff factor. So this is how all these three equations would be modified in case of abnormal colligative properties. This is how the Van't Hoff factor is introduced in all these three equations, right? So in numericals you would be using this Van't Hoff factor. When the numericals are on these abnormal colligative properties, you would be using these relations. Now let's just, since I said that Van't Hoff factor is for abnormal colligative properties, right, and this calculates this using Van't Hoff factor we can calculate the extent of association and dissociation. Now let's first see how it accounts for the abnormal colligative properties or the colligative properties. Van't Hoff factor I is given by, is the ratio of the observed value of colligative property, right, divided by the normal value of colligative property, right? And observed value we know is, in case of sodium chloride, observed value was when the particles dissociated into sodium and chloride ions, right? So this is the observed value where the particles has increased, right? And the second case was when the particles reduced, it formed a dimer. So observed value here was this one particle. So the particles have increased, the particles have decreased in case of association. This observed value has decreased, right? And in case of dissociation, observed value has increased. And since we know that the colligative property is inversely related to molecular mass, so here the normal one is below. So since molecular mass is inversely related to colligative property, the I factor, which is Van't Hoff factor, would be, we can write the same as below, normal molecular mass upon experimental molecular mass. And we know that in case of association, right, in case of association here, the normal molecular mass is less compared to experimental, right? And in case of dissociation, the normal molecular mass is greater compared to experimental, right? So now let's just see the value of I, how it varies with association or dissociation. We said, right, first we will take the case of association, where the two molecules of acetic acid associated to form a dimer, right? In that case, when it associated, the observed value of colligative property was reduced. Why? Because the number of particles reduced when two molecules of acetic acid formed one molecule, one bigger molecule, right there. So two molecules have changed into one molecule. So particles have reduced. Observed value has reduced, right, compared to theoretical value. So observed value of colligative property was in case of association was 1, where two particles are combining to give you one particle, and the normal value was of colligative property was due to two particles, right? This. So here it would be I would always be, since this denominator is greater than this numerator, right? Normal value is greater than the observed value, so I would always be less than 1 for cases of association. Now let's see the dissociation, wherein sodium chloride, and let's look at it from here also, from this perspective, from molecular mass. Since acetic acid, 2 molecules of acetic acid has changed into a dimer, right? 2 molecules formed a 1 molecule of a dimer, right? So here the molecular mass, the normal molecular mass was for acetic acid was 60, right? And for dimer it was 120. So if you put, let's calculate the value of I here. I would be equal to, the normal molecular mass was 60, right, and observed was 120. So I was 1/2. Here also it's 1/2, here also it's 1/2. So I would always be less than 1 for case of association, right? Now let's take dissociation. Dissociation was when sodium chloride dissociated to form sodium ion and chloride ion. Here it was 59.5 and 29.25, right? So now let's first calculate the value of I based on the first formula. Observed value was due to 2 particles, right? So observed value was due to 2 particles, colligative property, and the normal value of colligative property was due to 1 particle of sodium chloride, 1. So I would always be greater than 1 for case of dissociation. Now let's calculate it from the molecular mass concept. The molecular mass, normal molecular mass was 58.5, right? And experimental was these two dissociated to form sodium and chloride ions, and it was 29.25, which is around 2, right? It's same as above. So I is greater than 1 for cases of dissociation. We write it as I is less than 1, for association of molecules, I is always less than 1, and for dissociation, I is always greater than 1. Just remember this, the value of Venn Hoff factor in case of association and dissociation, right? Now let's calculate the degree of association or degree of dissociation. We'll derive a relation, right, between the number of molecules dissociated or associated and Venn Hoff factor in this. So degree of dissociation is number of moles of solute. First is degree of association, which is represented by alpha, and it is number of moles of solute associated divided by the total number of moles of